Hello friends, welcome to my channel and let's start with MATLAB Simulink video for today, that is Class C commutation circuit in power electronics. Now here we will start our Simulink from this icon above, and now you can see the Simulink library browser. You just have to press Ctrl N or just go to File, New, Model, and this is our Simulink model that we'll be having throughout. uh, First we'll do is save this project, save this model. I'm saving it as practical 6 is the same, this, and make sure that you have your library icon besides you for quick access. And done. Okay, so most of the blocks that we will require for today would be in sim power systems under power electronics or elements or measurements, and that's what we'll be using. So let's start with Class C commutation circuit. In Class C commutation circuit, the first thing that we see is a thyristor. There are two thyristors. So just drag thyristors from here. Again, drag a thyristor from here, and we'll just arrange it. To rotate these thyristors, we'll just press Ctrl R. Remember, it's Ctrl R, not just R. Just R is for zooming in and out. Okay. Now we have a detailed thyristor over here. We need elements because we need a resistor. Resistor is not available directly, so we'll use this series RLC branch. We need two of them, two resistors and one capacitor. So even the capacitor we can manage through this. So we need two resistors. So here we will select R, and the value here given is 6 ohms. It can be random to you in the experiment. 6 ohms again. So these are two series resistors, and this is a capacitor. Capacitor value needs to be calculated, but here we have it around 14.44 microfarads. Okay, and again Control R, and we are done with the basic circuit elements for now. All we need is a source, so we'll go for electrical sources. Remember that if you do not find any component, just search it directly in the search tab. You'll just get it. This is what DC voltage source. And we'll take it as around 100 or 120 volts as you wish. And remember here in Class C commutation circuit we have DC voltage source, not an AC voltage source. And we'll just go on making the connections. This is anode, so anode should be connected to the terminal. Okay, so we have all our connections. This is the negative supply, and the gate needs to be applied with pulses, so we'll have a pulse generator. I'm unable to find pulse generator, so pulse, just search pulse, and we have pulse generator. We require two such pulse generators, so one pulse generator for each. Use Control R. Pulse generator is connected. just neatly organizing this circuit. So pulse generator period for now 2 seconds is fine. Yes. Here we'll add a delay of 1 second, that is after half the time this SCR will be turning on, and pulse width would be around 10%. 10% is like the idealish amount of pulse width we can give. And we're done for now. Now what we need to do is we need to add the measurement parameters. So here we require a current measurement that is across the resistor, and we need a voltage measurement block, current measurement block. Okay, so current measurement block, remember, across the resistor, that means we have to take it a series with the resistor. Since both resistors are 6 ohm, there is no difference in the resistance, but if there is different values of resistors given, remember that we'll be measuring current mostly across the power resistor, the resistor that will be basically with least amount of ohmic value. Make sure it's well connected. It's connected, and this voltage measurement block would be rotated and connected over here. And now for the final, we need a scope. Just type in scope and you will get a scope. Remember that this scope has just one channel, so we'll have to open the scope, go into this tool thing, parameters, number of axes. If we have voltage, we have current, so, and we have pulses. So let's go around 4. We'll change it later if you want to. We'll just widen the scope up a bit. Yes, that's nice and tidy. And our capacitor voltage would be here. Current would be second. And remember the order that you're putting your current and voltages in, because that's really important when you are actually looking at the graphs later. Close this window for now. Then use this, and we'll use this for 2 pulse generators, and we'll check the SCR parameters in a while. So let's just check how our circuit is performing. And yep, the connection. So we have a screen over here. Just to auto scale everything, just click this binoculars, and we have some activity going on around here. Auto scale. We'll reduce the frequency a bit because I guess we're not able to see much effects in this. So we'll just make the period as 0.2. Pulse width will be same. Okay. And for the other pulse generator, our period would be 0.2 and pulse delay would be 0.1. Let's try now. Okay, now we are able to see few pulses over here. So here, as we can see in our, we have to keep our circuit diagram next to us when we are evaluating. The first is the capacitor voltage. So observe that the capacitor voltage is going from negative 120 volts to positive 120 volts. So so this capacitor voltage is basically the charging and not discharging, it's charging in the positive and the negative direction. So here we have wrongly put electrolytic capacitor, but in actual scenarios there are actual ceramic capacitors with dual polarity. So the second graph that we see here is the current graph. So if you see, this is connected to a current, that is current through the resistor. So this is when the SCR1, that is okay, here it is detailed thyristor, just the detailed thyristor, that is the first thyristor that turns on. This is the current that is for the first thyristor. So for the first thyristor, notice that when we switch the thyristor off, there is a huge current peak. This current peak is because of the charging of the capacitor through the like charging of the capacitor in the negative direction through this resistor. So at this point of time, thyristor 1, thyristor 2, both are switched on, and then there is a huge current flow through this particular resistor. While when the thyristor is turned on, the first thyristor is turned on, there is just the normal current, because the same thing is happening through the other resistor. Next we have gate pulses. For this gate pulses, we are not able to see the top or the bottom portion. So what we do is we go to axis properties, and here by common we know that it's from 0 to 1, so we'll just keep our axis bit above 0 and 1. So this would be minus 0.1 or the minus 0.2 to 1.2, that is slightly above and below. So this is how I get a clean, neat waveform. So again, here axis properties 0.2 and it's 1.2, and we get these clean waveforms. So here we can do the same thing over here too. We can take it all the way to 45 or something like that, so that we are able to see how the waveform is actually being affected over here. So this is how the capacitor and all the waveforms are. Now we will look at how the current through the SCR flows. So remember that this E, we'll just add one more axis to it. We'll make our axis 5, apply, and this E terminal is what gives all the details of the SCR. What did I do? I get the oscilloscope back to its origin. So E terminal of the SCR will give. The reason why we are concentrating on this left part of the circuit is because that the right part of the circuit is just a circuit, a turn off mechanism. This is basically our commutation mechanism for our commutation circuit right now, and while the left part is the actual power part, so that is where huge currents would be flowing in actual scenarios. So now if we run again, the simulation is completed. We open the oscilloscope, do the auto scale, and here we will get the SCR current and voltage across the SCR. We won't be able to differentiate it much here, but I'm sure we can estimate. So this is going around 120 volts. So that means the pink waveform that we are looking at should be the voltage waveform, that is the voltage across SCR waveform, while the yellow waveform should be the current across SCR. So we can use a mux, a demux, to perform the task of actually separating these two waveforms, and that would give us a better idea of what we are doing. But let's just check if we can use that demux, and here it is. So we'll just drag this demarks over here. I hate this. Okay, just increase the axis from 5 to 6 axis up. Okay, and just delete this. Okay, and here we are with the blocks. Now we have a clear distinction between what's our current and what's our voltage. So this is clearly the voltage that is going around 120 volts. Access properties. We'll just verify it. So we'll take it 130 from okay, apply. So from -5 to 130. So that is clearly our voltage. From -1 to 130 again. We'll just do that. Okay, so this is a negative spike. This is appearing because of the capacitor that is appearing across the SCR when it's being turned off. So remember that the SCR voltage basically represents if the SCR is on or off. So if the SCR is off, there will be full voltage that is appearing across SCR. So don't be mistaken for the high peak. It is there is voltage across SCR because it is off. So this is the off state of the SCR. So this is the off state of the SCR and this is the on state of the SCR. So if you just drag a line from here to here, see when the SCR is off there is no current, and when the SCR is on there is a lot of current. So when the SCR is being turned off, like at this point of time, so there is this negative voltage of the capacitor that is around -120 volts that is appearing across the anode cathode region of SCR, which is why there is the turning off mechanism of the SCR. So this is how we can, this is basically pretty much analysis of the waveform. So let's just wrap it up with all the waveforms. So the first waveform that we are observing here is the capacitor voltage. Capacitor voltage is being reversed every time you switch on or off the SCR. So it's plus 120 in one cycle, minus 120 in other cycle. It depends on how you're measuring the voltage. When the SCR is turned off, there is a huge spike of current through the resistor. That is because of the discharging of the capacitor. And this is basically the current waveform of the SCR. So when it is turned off, the current goes to 0. These are the pulses across the SCR. So they are pretty much self-explanatory. Then we have, remember not to operate your SCR at very high frequencies because sometimes it just cannot turn it off. So just go with the pulse values that I've used. Then this is the current through the SCR. So when the SCR gets turned on, so when it is just turned on, there's a huge spike through the SCR. So remember, when SCR is turned off, there is a spike through the resistor, and when the SCR is turned on, there is a spike through the SCR. So this spike is because the SCR is currently discharging the capacitor as well as flowing current through the resistor. So this is this current plus around 120 volts that is appearing due to the capacitor going to the other resistor. So those two node currents get added up, and that is why there is this spike. Once the capacitor gets charged up, the spike just goes away, and then there is just normal current, that is the current that is V divided by R current that we'll be generally observing through the capacitor. And the last one is the SCR voltage, which goes negative. The negative spike indicates that there is a negative voltage appearing across the SCR. So now the common question that you are going to be asked by the professor is that why can't we see the SCR being turned off? So like, why are these sharp? So I don't know why the professor himself can't get it, but when we just zoom in, if we zoom in, you can just show this to the professor. Like, there is a turn off time that is being taken. Okay, so this is the turn off time that the SCR is going to take to turn itself off. So like you need to show this to the professor if the professor himself is not getting it. So you can use the zoom properties or just tell him that if you zoom it enough, you can get the thing. To zoom out, you just double click. So you single click to zoom in. This is for X zooming, this is for Y zooming. Y zooming you're never gonna use. Just use the X zoom to zoom use, and for zooming out, double click, and that's how you zoom out. And this is all about the graphs. And that pretty much sums our circuit. Remember that this capacitor calculation 1.44 microfarad is not the value that is given to you. It is calculated by a formula, and the formula usually involves the turn-off time of the SCR. So just open the detailed thyristor thing, and there is number capacitance, number resistance, and there might be uh, turn off time of the thyristor somewhere. Explore. So here I'm not able to locate, but the turn off time of the SCR is always given, and turn off time is what determines how the what the value of the turn off time, and the resistor value determines what the value of the capacitor is going to be. So turn off time of the SCR, resistor value, resistor that is in the opposite end, and the capacitor value is going are three parameters that you need to adjust, but you can't adjust turn off time. So resistor and capacitor values are the ones that you are going to help you turn off your SCR.